Hello. In this module, we're still talking about disinfection techniques. Today, we'll look at ultraviolet radiation for use at the household level. We'll look at both artificial radiation, which needs electricity and lamps to generate the energy, and natural radiation, making use of the sun's energy for solar disinfection. Ultraviolet radiation is one type of energy along the electromagnetic spectrum, where different kinds of radiation are defined by their wavelength. Ultraviolet has wavelengths in the 100 to 400 nanometer range, whereas visible light is in the 400 to 700 nanometer range. If we zoom in on this range, we can define some subcategories. The lowest wavelength we call vacuum UV. It only exists in the vacuum. But then we have UVC, or deep ultraviolet, where the germicidal peak at 260 nanometers is found. Then you've got UVB and UVA shading into the visible light spectrum from 400 to 700 nanometers. Now, in order to describe the efficacy of UV light against different types of pathogens, we need to first define the dose. And just as for heat, it's important both the intensity of the disinfectant and the time. So for UV radiation, the units used in the US, they use millijoules per centimeter squared, whereas in Europe and other parts of the world, the preferred units are joules per meter squared. Now, DNA absorbs ultraviolet light in the 200 to 300 nanometer range, and it has a large peak right at 260 nanometers in the UVC range. So most of the commercial ultraviolet systems target this wavelength then. And UVC has been shown to be most effective against bacteria, followed by protozoa and cysts, and then finally against viruses and bacterial spores, where you need a bigger dose to inactivate those kind of pathogens. Typically, a dose might be 400 joules per meter squared, or 40 millijoules per centimeter squared, to get good removal of even viruses and bacterial spores. Here you see a graph of the efficacy of UVC against different kinds of pathogens. Here we've got the dose and the log inactivation, or LRV, on the other axis. Well, the first thing you can see is that E. coli is very readily killed by ultraviolet. Very steep curve. And total coliforms, a related bacteria, are also fairly quick to die exposed to UV. Rotavirus takes a little bit more time to kill, but it's the Bacillus subtilis spores that take the longest time. Now, I mentioned that there was a standard dose of around 40 millijoules per centimeter squared. That's about there. So we can see that at this level, you would be having, more than 4 log removal of bacteria, almost 4 log removal of rotavirus, but only about a little bit more than 1 log removal of the Bacillus subtilis spores. There are a number of different ways to generate UVC radiation using lamps, which of course require electricity. Low-pressure mercury lamps emit light in a very narrow wavelength band of around 254 nanometers, which is close to that DNA absorption peak at 260. So this is a very effective way to target DNA. Medium pressure lamps generate a broader spectrum of UVC, so not only the DNA could be targeted, but proteins and other kinds of inactivation could take place. And then finally, LED lamps are currently under development. These would also be very focused at a particular wavelength, but hold out the possibility of generating UV radiation at a lower cost than mercury lamps. UVC is very effective in water. It's not impacted by changes in pH, though turbidity can shield microbes from the radiation. There's a modest effective temperature where a higher dose is needed at low temperatures, but it's not a major effect. There are many commercially available UVC systems used primarily in middle or high-income countries, kitchen scale systems with a small UV lamp. And there's some interesting research into developing versions of UVC treatment that would be suitable for low to middle income households. Here's one example, the Mesita Azul, which was developed in laboratories at Berkeley University and trialed in Baja California, Mexico. It consists of a small UVC lamp. It does need electricity, that outputs 1,200 joules per meter squared, so 3 times that conventional range of 400. And there's a bucket reservoir where water drains by gravity through the UV tube into a receptacle. And along the way, it passes in a channel here underneath the UV lamp. It's not in direct contact with the glass, but it's a thin layer so that the UV can come into contact with all the pathogens in the water. The flow rate is pretty high, about 5 liters per minute in this system. A recent evaluation found that it was very effective in the field. Water quality was better than the same households before the intervention, better also than control households, and better than households that were using other kinds of disinfection, like commercial filters. However, the exclusive use was pretty low at only about 40% of households. While the Mesita Azul system is still under development, there is another UV disinfection process that has been researched extensively over the past 30 years, both in laboratory and field settings. And this is called solar disinfection. Solar disinfection works simply by taking a clean plastic bottle, a PET bottle, and filling it with water, and then lying it on a flat surface, maybe a rooftop, and exposing it to natural sunlight for at least 6 hours, or if it's a cloudy day, for 2 days. After the sunlight exposure, the water is safe to drink. This SODIS technique, then, has been applied in more than 20 countries, and more than 5 million people are using it today. For more information about SODIS, visit the Swiss website or Fundación SODIS for applications in Latin America. Now, solar disinfection doesn't make use of UVC radiation, and that's because as sunlight passes through the atmosphere, all of the UVC, and even about 90% of the UVB, is absorbed by ozone, water vapor, oxygen, and carbon dioxide in the atmosphere. UVA radiation is less affected by the atmosphere. Therefore, the UV radiation reaching the Earth's surface is largely composed of UVA with a small UVB component. Clearly then, SODIS has to work differently than UVC disinfection since UVC isn't reaching the Earth's surface, thankfully. And it does so with 3 main mechanisms. First is ultraviolet B radiation can still directly inactivate cells. It won't be absorbed so much by the DNA, but other components within the cells, perhaps proteins, enzymes, can be affected. However, the plastic bottles used for SODIS, PET, remove much of the UVB, so unless special bottles are used, this is probably a minor effect. A more important effect is thought to be indirect inactivation through UVA radiation, where the UVA is absorbed by some intermediate species and then goes on to create reactive oxygen species like hydroxyl radical or hydrogen peroxide, which cause the damage to the microbes. Those reactive oxygen species could be generated inside the cell if the cell contains chromophores, which are typically present in bacteria cells, or it could be external through dissolved organic matter or dissolved iron. And then finally, heat can play an important role. Of course, if the temperature gets up to 60 or 70 degrees, we're entering the realm of pasteurization. But even at 50 degrees, there seems to be some synergy along with the effects of radiation. There are a number of factors that influence how effective SODIS can be. First, around the radiation itself, the sun height is important, and the higher the sun is, the higher the UV radiation level. And this varies with the time of day, of course, but also the time of year. So the maximum levels occur at noon during the summer. The latitude is also important. Radiation does not fall equally on the Earth, and there are 2 belts from 15 to 35 degrees in the northern hemisphere and in the southern hemisphere, where radiation is at a maximum. Also, the belt between 15 degrees north and 15 degrees south has quite high solar irradiance and is a good zone for practicing SODIS. Altitude, at higher altitudes, there's more radiation. UV levels increase by about 10% for every 1,000 meters in altitude. Ozone in the atmosphere does reduce UV, and ozone can vary spatially. It can vary over the year and even across the day. The ground can also reflect ozone. This is more important maybe for sunburns, but think about a rooftop reflecting radiation back into a SODIS bottle. And then finally, the depth of water in a water bottle is important because UV radiation is attenuated by water. So if the bottle were too large and the water column were too thick, then UV wouldn't penetrate to the center of the bottle. Also, characteristics of the water are important. When the water temperature reaches 50 degrees or so, there's a synergy, and only about 1 hour of UV exposure is needed. However, turbidity can negatively impact SODIS, and if the turbidity is higher than about 30 NTU, it's advised to pre-treat the water with filtration or perhaps coagulation and sedimentation. With all of the factors that can affect SODIS disinfection, it's not surprising that evaluations have shown a range of removal values. Most of the studies have been on bacteria, especially E. coli, and these tend to find 3 to 5 log removal units. Sequence studies have shown that Salmonella is more resistant than E. coli, and that Shigella and Vibrio cholera are relatively susceptible to ultraviolet. Studies on protozoa have shown slightly lower removal from 2 to 4 log units, and both Giardia cysts and Cryptosporidium spores have been shown to be inactivated. There are relatively fewer studies of viruses. The methods are more difficult, and they show a greater range from 1 to more than 5 log removal values, where we see that certain viruses like adenovirus and the indicator virus Phi are quite resistant to ultraviolet. Adenovirus is also resistant to UVC treatment. And other viruses, the human echovirus and the indicator virus MS2 phage, are relatively easier to disinfect with SODIS. One of the countries with the longest history of SODIS is that Bolivia, where since 2001, EAVAG and the Fundación SODIS have been promoting solar disinfection. First with pilots in Cochabamba, and then with broader uptake through NGOs, through the health ministry, through schools, health professionals, and women's group. However, a 2009 evaluation in Bolivia found that among those who had received SODIS training, only about a third of them were routinely using SODIS treatment. Concerns have been raised about exposing plastic materials to the sun for water treatment because of the risk that some chemicals present in the plastic could leach into the water. Now, antimony is a chemical that's used as a catalyst in the production of PET, but antimony only leaches into water at appreciable levels when the water's in contact with the plastic for many weeks or longer, or if the temperature exceeds 70 degrees Celsius. Now, this doesn't happen during SODIS treatment, since treated water is only in the bottles for a few days, and the temperatures rarely exceed 50 degrees. Adipates and phthalates are used as softeners in the production of certain types of plastics and packaging materials. For example, PVC, which is used in plastic pipes. And although these softeners are not particularly toxic, they do represent a threat to health if they're consumed in large quantities. However, adipates and phthalates are not needed in the production of PET, so they cannot leach from PET bottles into water. Aldehydes are formed when the plastic is heated in the manufacturing process for PET bottles. A laboratory investigation of the diffusion of aldehydes from PET bottles into water found that exposure to the sun has no effect on the concentration of aldehydes that could be measured, especially for acetaldehydes, though the concentration of formaldehydes does increase with the length of exposure. However, the concentrations of these aliphatic aldehydes remained far below the state regulatory limit for drinking water in all samples. Formaldehyde and acetaldehyde can be problems for bottled carbonated water because the higher pressure and lower pH within those bottles can result in aldehydes in stored water. But again, since the pressure and pH are more moderate in SODIS treatment, these chemicals are not found at levels of concern in SODIS-treated water. Then we have bisphenol A, a chemical present in some plastic bottles that is suspected to cause breast cancer. But bisphenol A is only an issue with polycarbonate bottles, polycarbonate plastic, and not in the PET bottles that are most commonly used for SODIS. Another approach to assessing chemical safety of water is not to look for specific chemicals, but to see if exposure to the water results in mutations in certain plant or protozoa or bacterial cells. So this is a genotoxic approach to water safety assessment. And some of these genotoxic studies have found that when water is stored in plastic bottles for long periods of time, like several months, cell mutations could be observed. But this happened with or without exposure to UV radiation, so while it might be an issue for long-term storage in plastic bottles, it's not directly pertinent to SODIS. And this is similar to what we've seen in those studies looking at leaching of other chemicals, various chemicals. And since SODIS involves neither long storage times nor high temperatures, studies at EAVAG and other institutes have not found any evidence that SODIS introduces any harmful chemicals to treated water. For more information, visit the publications page at the SODIS Reference Center. The link is shown on the page. So some considerations then for UV treatment are that first, it's highly effective, both UVC and SODIS, though UVC, being a more powerful energy, is more effective, especially against viruses and protozoa. And both UVC and SODIS are limited to low turbidity waters because particles can shield pathogens from the radiation. Furthermore, UVC does require electricity to run the lamps. If we look at SODIS, some advantages are that it's very simple to operate. It's also quite inexpensive. You need plastic bottles, but not much more. However, it's highly dependent on the climate, both in terms of daily and seasonal variations and different effects in different regions. And it does take a significant amount of time, more in the treatment than in the actual work done to fill bottles. An advantage of SODIS is that there's quite a low risk of recontamination because water is typically drunk from the same container where it's been treated, so less chance of recontamination. However, it's only small volumes of water that can be treated at a time in a batch of SODIS treatment. In summary, then, we've seen what ultraviolet radiation is today and how it works against different classes of pathogens. We've seen how UVC intervention works and how they can be adapted for household water treatment. Currently, most of the experience there is in middle and high income settings, but there's potential for application in low and middle income settings, especially as LED lamps come out. And we've seen the much more widespread practice of solar disinfection, SODIS, how that works, and how it is being applied in many countries in the world today.